everybody. Buenas tardes. Hola. ¿Qué tal? Welcome to session 7A on this first virtual but 7th E&E Congress here in virtually Madrid. Session 7A is on Warmix and low temperature technologies. Technologies that have been mentioned several times during this Congress, and it's one of the key topics, I think, for our industry right now, but also in the near future. First of all, let me introduce myself. My name is Anja Sörensen. I'm a civil engineer graduated at the Technical University of Braunschweig in Germany with late Professor Wolfgang Arand, and I'm working for Eurobitume, representing the bitumen industry in Germany. In my country especially, Warmix technologies, reducing temperature of asphalt pavement, etc., is high on the agenda. So I'm very honored to be able to chair this meeting and this session. Before we start with the presentations of 6 real experts on these topics, I would like to address a number of housekeeping issues. You are familiar with the Slido app where you can raise questions. We very much welcome your questions for the questions and answer sessions, which will always take place after 3 presentations. Please type first the name of the presenter you would like to address your question to, and then raise your question. Please try not to chat in the Slido chat. And if you have a comment to make and not a question, please start that with comment. That will help us to follow on what you want to raise in the questions and answers, and that will also help us to dedicate the questions to the respective and correct experts. Now, let's start with the first speaker and then a short introduction. The first presentation will be conducted by Dr. Fabrizio Leiva on a paper jointly published with Randy West. Fabrizio is currently employed with NCAT, the National Center on Asphalt Technology at Auburn University, Alabama in the United States, where he works as an assistant research professor. Amongst other topics, his research focuses on sustainable pavement materials. The presentation addresses a research project with the objective to evaluate cracking potential of asphalt mixtures, incorporating Warmix asphalt technologies, and just as well reclaimed asphalt shingles. So I'm very much looking forward to your presentation, Fabrizio, and for the technician to start it.
Hello. I'm going to present to you the results of a nationwide study conducted in the United States with regards to Warmix technologies and recycled asphalt shingles. The objective of this study was to evaluate cracking potential of asphalt mixtures incorporating Warmix asphalt technologies and recycled asphalt shingles, and to compare them against the hot mix companions. The main concern about this study was that asphalt shingles need higher temperatures during mixing to activate the binder that is part of the shingles. If we were to use Warmix technologies that typically tend to lower temperatures during production, that was the main concern, that activation was not actually happening of the binder from those shingles. So in order to conduct this study and evaluate these technologies, the experimental plan included 5 field projects that were selected in different states within the United States. And we conducted laboratory testing related to cracking. One was the bending beam fatigue test, energy ratio that was developed in the University of Florida, the overlay tester, semicircular bend test, and Illinois flexibility index. Here's I'm showing the 5 projects that were selected at different states, one in Wisconsin, the other one in Alabama, Tennessee, North Carolina, and Indiana. And we have a variety of technologies, 3 additive technologies and 2 foaming technologies. We also have a variety of virgin binders ranging from 58-28 all the way up to 67-22. We have different sources from aggregate and sizes ranging from 9.5 millimeter to 12.5 millimeter. pretty much all the mixes in the United States have a RAP or reclaimed asphalt payment. The minimum we had was 10%. And with regards to alpha shingles, those range from 2% all the way up to 5%. And those were the ones that we were mostly interested on. And I'm going to show you the majority of the results that were statistically significant. And because what we were looking in this study was for the warm mix technologies to perform similarly or better. Otherwise, we will be encountering negative effects. And that way we will have to start considering the use of the warm mix technologies in a different way. Fortunately, we were able to find that in most cases, for all these different tests that we conducted, the majority of those were similarly or better. And here's an example of flexibility index test results, where we were able to see for all the cases where the results were conducting the test on warm mix technologies, those results were better or similar. For instance, for the first one, Wisconsin, there was no statistically significantly a difference between the warm mix and the hot mix. But you will move to Alabama, Tennessee, North Carolina, those showed significant differences when going from the hot to warm mix. In at least in 5 different pairs, we were able to see that the warm mix technologies outperform the hot mix technologies, which it was good. We were looking for something similarly or better. Another results that we wanted to show are the overlay test results. And again, I'm showing in 3 projects. In total, we have 5. I'll show the next in the next slide. But you can see that in most cases, the results of warm mix technologies showed higher cycles until failure, which is showing that warm mix technologies are better performing mixes compared to the hot mix companions. But statistically speaking, only a few were significantly different or better. That was the case for one warm mix technology from Alabama project, the low volume warm mix, as you can see, established with a letter B. And then for the Tennessee project, we also found a significantly difference between the warm mix and the hot mix cycles to failure. And of course, that was a statistically significant difference. For the other 2 projects, we found a couple of pairs where warm mix outperformed the hot mix. But in most cases, we found that that was the case. For some of them, the variability didn't show as significant difference. But in a couple of cases, as denoted by letters C and B on the grouping, we were able to find that those were indeed different. And here I'll show you the summary of all the results, including the ones that I didn't discuss before. The first one is the bending beam fatigue test. In that case, we didn't find any significant differences for any of the pairs that we were comparing. We were comparing warm mix versus hot mix technologies. And for any of those, we were able to find differences, which is okay. I think as long as we didn't find anything negative or something that was below the performance that we were looking compared to hot mix technologies, that was okay. We didn't have any preliminary criteria to compare with in that case. No other test was the energy ratio. As well, we couldn't find any significant differences. And in that case, we do have some preliminary criteria to compare. And for most cases, all these warm mix technologies were able to be classified for medium to high traffic levels. And again, to show you the results that I discussed previously for the overlay, for the flexibility, those showed significant differences. 3 out of 10 pairs for the overlay and 5 out of 8 pairs outperform, or the warm mix technology outperform the hot mix technologies. And in the case of flexibility index, there was preliminary criteria. All of them failed that criteria. However, we were expecting that because those mixes had wrap and recycled asphalt shingles. So that was expected. And the last test was the semicircular bend test, and we didn't see any significant differences. And again, that was okay because we were hoping to have a similar or better performance. And a number of mixes were classified up to level 1 or level 2 traffic, not as good as the energy ratio results that we observed before, but at least we're observing that we can have some classified in high traffic or high volume. So in conclusion, we were satisfied with the results. We didn't observe any detrimental effects on cracking resistance based on those 5 different tests that we conducted. And that was part of what we were looking when we started this study, because the concern was that the warm mix technologies were going to lower the temperature during production, and that may reduce activation of the asphalt that is part of the asphalt shingles. And we were able to observe that was not the case. In fact, we were able to observe that in most cases, warm mix technology help increase cracking resistance, and that's promising in regards to these different materials, not only for wrap that has been observed in the past in the literature. There are many different publications that are already consider the combination warm mix and wrap as a way to go in terms of performance. But now we were able to observe that that can be the case when we add recycled asphalt shingles. And with that, that's all I have, and thank you very much.
I am Mario Jair from Argentina, and at first I would like to thank the Eurobitume Technical Committee for selecting our work for an oral presentation. It's a pleasure and really an honor. The content of the paper is divided into 2 parts. Firstly, a brief summary about our experiences in the use of warm asphalt mixes in Argentina. And secondly, the latest development made in lab, combining warm mix technology with the use of different types and rates of wraps. As background, I would like to comment that in the last Eurobitume Congress, the 3 parts of the paper presented there were about one wrap case of studies. Regarding the experiences in Argentina, I would like to say as well that the warm mix technology were introduced in 2010. More than 100,000 tons produced, lay and truck on heavy traffic highways. In our countries, and following the latest trends, all the experiences so far had been with chemical additive or via chemical additivation. Most of them associated with the use of the P&B low temperature grades. And due to the increased availability of wrap and from the special asphalt mixtures, the one wrap option is interesting for the future. Here, a summary about our experiences use warm asphalt mixtures. Paving and modified low temperature binder are available in Argentina according to our local standards. Personally, I was involved in more than 80,000 tons designing and laid from 2010. Temperature reduction up to 30 Celsius don't affect the properties of the asphalts. And volumetric parameters such as air voids, etc., of warm asphalt performed via low temp grades or low temperature grades don't have the same correlation with their mechanical properties as when using paving grades or conventional modified bitumen. Moving on the one wrap studied in the lab, these are the 6 one wrap options designed for dense and 2 thin mixtures. The dense mixes adding 25% of wrap from an all dense mix with PMB. The thin ones adding 44% of wrap from an all stone matic asphalt also with PMB. 4 types of binders were used. A conventional CR30 bitumen that is one viscosity grade according to the local standard in Argentina and is a low temperature version. And on the other hand, E&E3, the most used PMB in Argentina, and again, is low temperature grade. Here you can see the bitumen characterization of the wrap, which was divided in 2 fractions. It is important to note the good elastic performance of the wrap binders as they come from mixtures based on PMB. Continue with the evaluation of material, the characterization of virgin asphalt binders used for the test. The following are the gradation curves of the asphalt mix design. In this slide, for the asphalt option using 25% of wrap. And here is the curve for the thin asphalt with 44% of wrap. Starting with the evaluation of the designing one wrap options, we decided to observe the resistance to water, which was evaluated by means of the indirect tensile test. As can be seen, the retained resistance was greater than 80% in all cases. We also decided to study the rutting performance using the well tracking amber test. The slide shows the behavior for the dense mix with conventional binder and its low temperature version. Here, for the same asphalt mixture, but based on AM3 and AM3 low temperature. And finally, the thin asphalt mixture based on AM3 and AM3 LT. The findings of the development of one wrap option evaluated in lab are as follows. We could see that reduction up to 30 Celsius don't affect asphalt mechanical properties. Regarding water the mass performance, the retaining resistance was always greater than 80%. In terms of the rutting performance, in all cases improved due to the use of wrap in all asphalt evaluated regardless of the type of bitumen used. No significant change in rutting behavior were observed for the use of their low temperature binders. With regard to amber test performance, the use of low temperature grades showed greater deformation than those designed with conventional CR30 and AM3 grades. But in all cases, deformation limit is not reached and no water damage was observed. And again, the volumetric parameters, air voids, etc., in one wrap performed via low temperature grades don't have the same correlation with their mechanical performance. So a better knowledge about low temperature binding effects should be considered, and a possible new approach considered as well about one wrap design. And what is the future of this? It's clear that one wrap are a promising option. In our opinion, asphalt standards or one mix specification should consider the type of one technology used and obviously the type of wrap used as well. We need to move from recycling to reuse due to the higher value of wrap when coming from all special mixtures. Production and compaction temperature rate should be part of the asphalt mix design in all cases. And a scale production of one wrap will generate more information, which will allow adjustment in protocols and standards. Thank you very much for your attention, and I open to questions.
So thank you very much, Mario. And apologies to everybody for these slight difficulties. That's technology. I'm very grateful that we have a virtual Congress and all these opportunities, but then sometimes there are some tricks in the background. You just heard a presentation from Mario Jaye on a paper that he published together with Rosanna Marcozzi. Mario has nearly 30 years of experiences in the asphalt production and road construction industry. He is the Vice President for the Permanent Asphalt Commission of Argentina, member of the board of the Argentine Association of Roads, and happy grandpa to a granddaughter, as highlighted in his vita. Thank you very much, Mario. Thank you very much to everybody for your kind understanding of these difficulties. Let's cross our fingers that that would have been all. The third presentation, and afterward we will go into the question and answer session. So thank you already for raising your questions in Slido, is made by Thorsten Butz, head of the Analytics and Bitumen Additives Development at Sasol Wachs GmbH in Hamburg, Germany. That's easier for me to pronounce. As such, both technology development as well as technical supports are on his daily schedule. The presentation addresses a paper jointly published with Carsten Oelkers and Dr. Knut Johansen on results from development work for Warmix asphalt additive that provides a solution for the problem of residual moisture on the aggregates when you're using Warmix application technologies, especially when producing at extremely lower temperatures. Many research papers reported on increased water sensitivity of asphalt, which is caused by the residual moisture. I'm interested in that presentation. Thank you.
Thank you very much for the introduction. Dear ladies and gentlemen, I have the pleasure to speak about optimizing warm mix concepts with combination products. It is generally accepted that warm mix asphalt is a key technology for a sustainable future. It allows saving resources, decreasing the carbon footprint of asphalt paving, and improving the health of the workers by reducing the emission of bitumen fumes and aerosols. But there are also technical challenges. The main challenge is residual moisture on the aggregates. This may lead to insufficient binder affinity and increased water sensitivity of the asphalt. This was often observed and reported in lab research, but still is unclear for the field. Nevertheless, the general recommendation is to add hydrated lime or liquid adhesion promoter to overcome this challenge. Our development concept had to fulfill the following demands: improvement of compactability at lower temperature to allow warm mix, improvement of the binder aggregate affinity, and no significant effect on the binder characteristics should take place, such as stiffness and low temperature flexibility. It should be a one-pack additive, which is convenient for logistics and use. Our final solution of this development work is a solid compound comprising Fischer-Tropsch wax, a petroleum-based component, and an affinity improving substance, which can be used as adhesion promoter. Our concept was validated with the following test program: compaction at different reduced temperatures, laboratory simulation of Warmix asphalt production, and finally water sensitivity testing, applying dynamic indirect tensile test with and without water storage. For the compaction tests, we selected the Marshall method and used in stone mastic asphalt 8S according to German regulations. 3 different mixes were produced. A hot mix reference using a standard polymer modified binder 25-55-55. The second was the same but included 1.5% of a standard Fischer-Tropsch additive, the well-known Salsobit. And the third, also the same mix but including 1.5% of the new combination additive. Compaction was done at 145, 120, 180 and 60 degrees. The diagram shows that equally both additives reduced the compaction resistance and resulted in improved density. And we can see that at 120 degrees, we obtained the same density as with the hot mix reference at 145. This means 25 degrees temperature reduction were possible without compromising compaction. We can also see that the new combination additive gave the best compaction at 100 degrees and below. Warmix asphalt production at reduced temperature may leave residual moisture at the aggregates. But how can this be simulated in the lab? Laboratories generally are working with completely dried aggregates to get the mass balances correct. Our solution was as follows. The aggregates were dried, weighed, heated to 25 degrees lower temperature and were pre-mixed. Then 3% water were added. About 1/2 of the water evaporated and the rest was retained at the aggregate surfaces. Immediately after the water, the binder was added and the asphalt was mixed. Again, an SMA 8S was used and it was compacted with a roller segment compactor. The reference hot mix was produced at 145 degrees and again with the polymer modified 25-55-55 bitumen. The Warmix asphalt was used the same binder but including 1.5% of the new additive and with the water addition. This mix was compacted at 120 degrees, that means 25 degrees lower. And again, we obtained equal compaction, equal density, which proved the first results. For water sensitivity testing, 100 millimeter cores were drilled out of the compacted slabs. 1/2 of the specimen was dried underwater for 72 hours at 40 degrees and reduced pressure. Then dynamic indirect tensile tests were performed at 20 degrees with 10 Hertz and 2 different stress levels. 1/2 dry storage and 1/2 with water storage. The diagram and the photograph shows the principle and the setup of the test procedure. This diagram shows the fatigue results for the dry stored samples. We plotted the number of load repetitions until observed macrocracking over the initial elastic strain. We see that the fatigue functions were equal with slight benefits for the Warmix. The Warmix is shown in the blue dotted line. Jumping to the water stored samples, we see quite similar results. Equal fatigue functions with slight benefits for the Warmix. This result shows that it is possible to produce Warmix asphalt without compromising the water sensitivity. Finally, my summary and conclusions. A Warmix additive with binder aggregate affinity improvement was designed, which addresses the residual moisture challenge. It allows similar compaction at 25 degrees lower temperatures. The fatigue performance of the asphalt was slightly better compared to the reference hot mix asphalt. Meanwhile, this concept was successfully proven in field tests. So in summary, a solution for temperature reduction without compromising asphalt performance was developed. Thank you very much for your attention.
Thank you very much, Dr. Butz, for your presentation. I'm now happy to start the first questions and answers session. And I'm delighted that Fabrizio, Mario, and Torsten will join me for that. Thank you very much for posting your questions already in the Slido. And just remember, the Slido is for questions. It's not for a chat. I would like to, I understand the interest that there is on a number of questions, and I'm very happy to address those in this question and answer session as well. Once again, apologies, especially to Mario for the late introduction of that.
No problem, Anja.
Let me compensate by asking the first question to you. There's a question from on the experiences using REP for SMA designs in Argentina, and that question has been asked by Gonzalo Oroz. So maybe you can answer that question first.
Yes, okay. Thank you very much for your question. And well, we are starting with that. Yes, based on the concept that we need to reuse all special asphalt mixes in the design of the new ones. So we are starting with that. But you can see in my presentation, during my presentation, the MAC A10, that's a special wearing course as well, similar to the stone mastic asphalt, because it's a discontinuous or not continuous gradation, yes, of the asphalt mixture, so providing excellent macro texture. But it's a similar concept of the stone mastic asphalt. But we are starting with that at the laboratory level, and the idea is to conduct some trial next.
Okay, thank you. What are the drivers for Warmix asphalt technologies in Argentina?
Sorry?
What are the key drivers for Warmix asphalt technologies in Argentina?
Well, really, the Warm technology was introduced in 2010 in our country, and the initial segment to work with that with the concessionary or the private owner of the highways, mainly because in general they need to work during the night, yes, with cold temperatures in winter, and mainly as well taking into account the needs to have one more extensive window, yes, of work, you know, because all these type of the tasks are produced or are conducted during the night. So, and for the reason as well, our experience is mainly based on the use of the PMB, yes, low temperature binder. Why? Because in general, this segment, this road segment, use PMB for your jobs in general, you know, and for your surface, you know. So for the reason, our experience is based on the PMB and low temperature grades of PMB.
Mm-hmm. Thank you very much for that. Can you also give us an impression of the volume or the rate of Warmix asphalt technologies in Argentina right now? How important they are? Well,
it's not sufficient in my opinion. It's not enough in my opinion, you know, because again, it's related with the tax of the private owner. So at the moment in Argentina, we are passing for one non-good economic situation, and this particular situation affects to the production of the asphalt in general, For the new technology, well, new is a way to say, you know, technology, because we have 10 years of experience. But I think that very, very soon we need to reintroduce this technology, and at the same time combining with the use of the RAP, because the RAP use is in our agenda in the same way that occur in the different countries around the world.
Thank you very much, Mario. I would like to ask the next few questions to Fabrizio. There's quite some interest, a number of thumbs up in the Slido on questions about the aggregates, bitumen mixing and compaction temperatures. You already answered in the Slido to that because these questions were so urgent, but maybe you can just share in the wider audience orally what you replied to that question. So this is about the aggregates, bitumen and mixing and compaction temperature. Then there will be another question about the bituminous binder used in shingles, whether you looked at that in detail, both from, I think, a technical perspective as well as from the perspective of HSE, especially with regard to the IARC recommendations on oxidized bitumen emissions.
Yes, in regards to aggregate sources, pretty much of those were local sources from all these different states within the United States. And the aggregates range from granite, limestone, gravel, with the idea to cover the majority of the most commonly used aggregates in the United States. So those were the sources. And with regards to temperature or mixing temperature, we were able to reduce, or at least the producers were able to reduce temperatures with the Warmix technology between 50 to 70 degrees Fahrenheit. They were using different types of technologies. The majority were using additives, and there were a couple that were using foam technologies to reduce those temperatures. With regards to the shingles, yeah, we were able to characterize a very simple characterization, just the performance grade of those shingles, even though it was a little bit difficult because they were quite stiff. They were in the range of 110 to 120 degrees in the high end performance grade. With regards to emissions, we know that there may be some issues since to produce hot mix asphalt requires elevated temperatures or more or higher temperatures during production. The same case with DRAP. So since we know that warm mix technologies have worked really well to compensate and with the amount of RAP, and also to reduce emissions during production and even during compaction, that's something that that was a secondary objective to also minimize any potential emissions. I'm not really aware what is the name of the recommendations or the institution.
IARC, International Agency of Research.
No, and that one, yeah, we didn't consider any of those because that was not part of the scope. But the one of the ideas was to help reduce emissions with warm mix technologies, but we didn't account for those. That was not part of what the proposal of the agency sponsoring the study.
Okay, thank you very much. Let me go to ask a few questions to Thorsten Butz now, and there are more questions coming in. That's very interesting. I would like to raise two questions to you as a beginning. The first one is, first of all, a brilliant presentation, and I think you can all agree with me that applies to all three presentations we had. So that was a brilliant presentation. The question is, have you considered short-term aging during the asphalt specimen production? And another question I would like to share with you is on Slido, whether you think that a chemical reaction would support or would help to get rid of the water on the remaining water on the aggregates, maybe as an alternative to it's called wetting agent, maybe it's an adhesion agent. So one is about short-term aging, and the other one is about a chemical, and you're a chemist, I know, so a chemical reaction to get rid of the water on the aggregate.
Yeah, I start with the second one. That's very interesting for a chemist indeed. I haven't thought about this, but it's an interesting concept, and I think somebody should try to use it. There are different options for chemical reactions, and that's an interesting idea for the future. Yeah, regarding the short-term aging, we didn't, in our experiments, didn't include something like that. We just have the short-term aging, which happened during our experiments. Just when preparing the mixes, heating the binder, and doing the asphalt mixes. So it wasn't specifically addressed by other means in this case.
Okay, maybe I can ask a third question that was just shared. When you compacted the hot SMA versus the warm SMA, you used a segmented roller compactor in the laboratory, did you apply the same number of turns of rolls for both mixtures, or did you have a variation in that?
I didn't personally
pretty detailed.
Yeah, I didn't personally run this experiment, so I think it was the same number of compaction rules in this case.
We do have a little bit more time, so maybe I can ask another question to you, Mario. The question is from Anonymous. It's, can you give us detailed information about the difference of F10 and SMA, please? You said similar, but similar is not the same. Have you looked at the durability of these mixes?
Okay, same for your question, Anonymous. Yes, unfortunately, sometimes it's not possible to see who are. Okay, well, when I talk about the F10 asphalt, is the most extensive surface, yes, a special surface that we use in Argentina. Yes, it's based on non-continuous gradation, but in comparison with the stone mastic asphalt, less bitumen content. Yes, in general, 5.2% in comparison with the stone mastic asphalt, that is more than 6 in general. No use of fibers, yes, that's we use in stone mastic asphalt, and in general the air content is higher, yes, in comparison with the stone mastic asphalt. We are talking about 6%, 6.5% versus 3 and 4%. So it is the similar asphalt mixture in terms of the macro texture, you know, and in terms of the low noise, etc., the functional issues. But you know, it's not the design process that in general the stone mastic asphalt is a volumetric design process, and in this case, for the reason I say similar and not the same, you know. But we are starting with as explained, with the design of the stone mastic asphalt as well, based on low temperature or combining low temperature technology with the use of RAP.
Okay, thank you very much, Mario. And
Thanks,
thank you everybody for the questions that you raised. There will be more, I'm pretty sure about that. I would now like to turn to the second section of this session, 7A. Thank you very much to Fabrizio, Mario, and Thorsten. And start with these presentations. We will have another question and answer session at the end of that. And if the time allows, we will have, and there will be no technical issues anymore, then we can also take on board questions to the first section of presentations as well. And you are always free to contact the authors directly. Now, the first presentation in the second section of session 7A will be held by Professor Fernando Moreno Navarro of the University of Granada, extremely experienced in this Congress, having been a session chair, and he submitted so many papers to this Congress. Fernando is, in his professional career, has already received numerous awards, such as the Robert Lermy Medal of RILEM in 2018, but also Research and Innovation Awards by AILA, PTC, ASEFMA, or the University of Granada. The paper he's now going to present on is based on joint work of a group of 6 authors, and pretty sure that Fernando will give you all the names, on the long-term performance of sustainable asphalt mixtures under high volume traffic. I'm interested to learn more about that. Thank you.
Good afternoon to everybody. Sustainability has become a crucial issue to guarantee a viable transition from highway to smart roads. In this respect, future asphalt materials must be manufactured using eco-friendly techniques, and they must present a good long-term performance to minimize the environmental and socioeconomic costs associated with the operation required for pavement construction and conservation. Based on this consideration, the government of Andalusia, in collaboration to the Laboratory of Construction Engineering of the University of Granada, are working together with other companies from the road sector to develop MASAI, sustainable, automated, smart asphalt material, which are called to be the materials for the next generation roads. MASAI are high-performance and functional asphalt materials which are manufactured at the maximum temperature of 140 degrees. They are modified with reclaimed polymers. They are manufactured with reclaimed asphalt or valorized by product or wasted from the industry, and they will incorporate sensor and other devices which send, receive information to offer new function that will improve safety, traffic flow, control, etc. Based on the need that the MASAI will meet, we can obtain different grades of MASAI. In this respect, the first 2 conditions are mandatory, and if the MASAI meet with a third one, we consider it a MASAI grade 1. If in addition, this MASAI incorporates sensor and other devices that make it automated or smart, we consider a MASAI grade 1+. If the material meet with the 4 material conditions, we consider a MASAI grade 2. And if it meet with the 5 conditions, including the sensor and the other devices that make it automated or smart, we consider a MASAI grade 2+. This presentation summarizes the result obtained in a research project in collaboration with Construcciones Pérez Jiménez, which was focused on the application of a MASAI grade 1 as an overlay for the rehabilitation of a road subjected to a high volume of traffic and severe climate conditions. The MASAI grade 1 used was a high-performance asphalt material manufactured at a maximum temperature of 140 degrees and with a crown rubber modified asphalt bitumen. During the design of this material, different rheological tests using DSR were performed to assess the mechanical performance of the crown rubber modified bitumen used for the manufacture of the mixture in comparison to a traditional polymer modified binder. Workability and performance tests were carried out at different temperatures and using different types of additive in order to select the optimal manufacture condition. After that, different tests were used for the asphalt mixture design and quality control. The MASAI grade 1 was used for a rehabilitation action on the I-92 highway in South Spain, where it must withstand with extreme climate conditions and high traffic volume. In addition, the condition during the construction was very adverse because this material were applied after long hauling distances in a thin layer and during night works at low temperature. It will also withstand with a difficult environment during the service life because the original pavement was very deteriorated due to the traffic, but also because during their service life, they will in constantly presence of around 5 months each year of salts and other fundants and the pass of snowplow trucks. So we can say that this material will try in the best trial condition because was the most exigent. After that, we after the construction of the trial section, we made an exhaustive control during manufacture, laying, and compaction that includes thermal control, mixture control, emission control, and layer control. Results obtained in the rheological test demonstrated that the chrome rubber modified bitumen offers a more elastic performance, especially at high temperature. Workability test demonstrated that it was possible to reduce the manufacture temperature by 25–30 degrees without having an impact on the mechanical performance of the material. The Masai Grade 1 design offered a high resistance to plastic deformation and a lower water sensitivity, as well as a high resistance to particle loss in a similar degree to traditional high-performance hot polymer modified mixtures. On the contrary, they offer a slightly lower stiffness than traditional high-performance hot polymer modified mixture, but a higher resistance to low temperature and fatigue cracking. Masai Grade 1 tested was successfully manufactured at 140 degrees, laid at 135, and compacted at 130 degrees. A reduction of around 20% in fuel consumption was observed, and the contaminant emission was also reducing in terms that range from 20% to 50%. The quality control corroborates the good performance of the Masai, especially in terms of long-term performance under fatigue cracking test. After 4 years, it is performing perfectly in spite of the deteriorated subjacent layer, the hard winter, and the high traffic volume that it must withstand. As conclusion, we can say that the laboratory design of the mixture revealed that Masai Grade 1 led to a mechanical performance comparable to that recorded for traditional high-performance hot mixers, in spite that they were manufactured with chrome rubber modified at 30 degrees lower than the hot conventional mixture. The study of reproducibility in plant demonstrated that Masai Grade 1 can be manufactured in a conventional asphalt plant and spread with conventional equipment. In addition, the cost overrun associated with the use of additives for lowering the temperature can be partially compensated by the reduced energy consumption in plant. The research project presented has demonstrated that Masai Grade 1 is a viable alternative to traditional asphalt material under best conditions. Thank you very much for your attention. If you have any question, you can do it right now or by sending an email to my email address. Thank you very much.
Now, here I am. Thank you very much, Fernando, for that. From high volume traffic, we are now moving on to urban challenges. The next presentation will be held by Carlos Solis Navarro, a chartered engineer at the ICE, Institution of Civil Engineers. Since 2016, Carlos has been performing the ground engineering lead role for the Ealing Sydney's congestion program. Carlos is very passionate about sustainable pavement technologies, and his paper describes the challenging conditions to deliver urban projects on the Sydney network, including an initial assessment of the performance of the Warmix asphalt used. Enjoy your first presentation in Spain, Carlos.
Thanks, Tania, for your introduction, and thanks Euroasphalt and Eurobitume for having me today. Today's presentation is for me another stop on what I call my sustainability journey, a journey that I started in the UK and I was able to continue in Europe. It is also a story for me of hard work, persistence, and to some extent success. There were other three elements really in this story, which were curiosity, innovation, and collaboration. My plan for today is to provide an overview of the E&E Sydney's congestion program, the environment and the framework in which we implemented Warmixes as our default asphalt mix, and then go through the different phases of the project, describing the main barriers encountered, the challenges, and how we resolve it. Finally, I will describe and will highlight the key actions moving forward. The E&E Sydney's congestion program is one of the responses of the government for the increasing demand of infrastructure. The population in Australia and in Sydney is expected to double up in the next 20 to 30 years, so that the demand of infrastructure. The program started in 2016 and is still ongoing. The main goal was to squeeze the capacity of the network by improving existing intersections or building new bus lanes, improving corridors. All of this work is to be undertaken in urban and already constrained environment. So we were seeking solutions, low impact, cost-effective solutions. Low impact meaning solutions that were disrupting as minimum as possible to the road users. Within this context, we identify that Warmixes could contribute to this goal. Warmixes will enable us to build quicker, therefore gain some productivity efficiencies, as for example during a night shift we will be able to lay 3 layers of asphalt rather than 2. But also we will get some environmental benefits as a result of reducing the energy required to produce the asphalt mixes. All of this will lead to a reduction in cost, first from the energy consumption side, and also, for example, in a reduction in traffic management, which is like a significant cost at the end of the day for these projects. Having this methodology in mind, we adopted for a number of projects. This shows an example of the solution. We have a widening, and then also we have some treatment within the existing carriageway. The thicknesses that we are talking is around 310 millimeters. So the Warmixes for the case of the rehabilitation within the carriageway was critical to be able to do it to undertake the job during night shift and open to traffic the following one. Another example, in the Stacey Street upgrade, we had the same widening and then some rehabilitation with similar thicknesses. So again, Warmixes was the only solution to undertake the job and without disrupting or closing the road. At the beginning of the program, we thought that just adding the word Warmix to the right of the type of mix, AC20, was sufficient, and just adding the requirement for Warmix in the specification. And it was quite promising, as we were receiving the constituent material report with the Warmix additive in it. However, when we were reviewing the laboratory test reports, we could identify that the compaction temperature of the asphalt mixes was still 150, similar to a hot mix. And therefore, there was a lack of communication or understanding from the contractor and supplier of the intent of the Warmix, of the use of Warmix. In order to calculate an equivalent compaction temperature, the Warmix compaction temperature is required to undertake some testing and reporting in accordance to an Australian standard. This is in the case of Australia. The goal here is to get a temperature that it will deliver the same performance of the hot mix. For this project that we were not able to get these temperatures, we liaised with the supplier, with the contractor, and we undertook all this homework before the delivery date. However, when the project started to go on site, I witnessed that the temperatures on site were still hot, as a hot mix. They were using the Warmix additive, but still they were manufacturing at hot mix temperatures. Investigating a little bit this problem, there was like a lack of communication in this case in between the contractor and the supplier plant. Having this in mind, we decided that additional information was needed on our documentation, specification, and drawings. So we started to add in all this all this testing required and in the specification. Additionally, on the drawings, we add this note, letting the contractor know that the temperatures has to be lower, and they need to follow this methodology to calculate this warm mix temperature. Doing this gradually, little by little, we end up having more projects with the manufacture and compaction temperatures lower to the standard, around 20 to 30 degrees less than a hot mix. What is more important, the performance was similar and was similar to a hot mix and conforming to the specification. That for us was the beginning of a new era and a great milestone for great achievement for the easing synthetic congestion program. A little bit of data from site. We undertook a trial with hot mix and warm mix at the same section with the same condition, and we had the similar result in terms of compaction and relative compaction and densities. So all of that as expected. We also try to report or to test, not to track the cooling rate of the hot mixes and warm mixes, but the methodology used had some limitations, and we were using just a probe to check the temperature at the top of the surface. Moving forward, in easing synthetic congestion, we have 3 goals. First, to be able to report program efficiency savings in order to provide more comfort to the suppliers so they can understand the gains from the warm mix. That is similar. This similar work has been done in the UK, where they were reporting program savings of 20%. We are also trying to report carbon footprint savings. That is similar to some work that is being undertaken or has been already undertaken in Spain. And at the moment, we are also trialing and in the use of warm mix with polymer modified binders. The gains will be more associated to the environmental side, to the program savings, as the thickness is just 50 mil thick. The main takeaway of this presentation is that collaboration and willingness of all parties involved are key elements for the implementation of this technology. The ESC is just a small example of what can be achieved if the right mindset is embraced. Let's then work all together, road agencies, contractors, consultants, suppliers, because a shift to a more sustainable pavement industry is possible. I would like to close this presentation without acknowledging the contribution of Luis Alberto Solís, a true legend of the pavement industry and my inspiration as a father. Thanks for listening.
Thank you very much, Carlos, for your presentation and the very personal closure. From Sydney, we are now moving on back to the United States, where this session started. Welcome, Dr. Xianghua Wu, currently assistant professor at the University of South Alabama in Mobile. Xianghua had worked at the Illinois Center for Transportation before and is an active member of numerous committees, for example, at the Transportation Research Board, TRB, and other institutions, and also serves as panel member for several national projects in the United States. Xianghua is presenting on behalf of a group of 4 authors to the paper on long-term performance of Warmix asphalt in the United States. Thanks for virtually at least coming to Madrid, Xianghua. Hope you can make it in live in the not too far future as well. I'm looking forward to your presentation.
Hello, everyone. My name is Xianghua Wu. Today, I'm very pleased to present our research. Our topic is about characterization of a long-term performance of a Warmix asphalt in the US. I also want to thank our co-authors, Dr. Shen from Pennsylvania State University, Dr. Zhang from Southeast University in China, and also Professor Mohanfen at Washington State University, and Dr. Mohammed at Louisiana State University. I'm going to starting with the very brief introduction to the Warmix asphalt technology. As you know that we have three major categories of the Warmix. The first one is the VAX additives. It is a long chain aliphatic hydrocarbon from the co-classification. As you can see, the photo here is going to be just wide rounded particles. And the second major one is going to be a chemical additives. It has many brands, many patents available on the market. It is a liquid agent. And then the third one is the foaming technology, which includes the water-based. When you have a 100% water mixed with the asphalt at a very high temperature, the water is going to be, become as a steam. It's going to increase the volume of asphalt. So in that case, we can reduce the viscosity of the asphalt binders. And the second type of the foaming technology, it is the water containing, which is the zeolites. It contains 20% of water. So when the zeolites mixed with the hot asphalt, it can also release the water into the asphalt mixture to reduce the viscosity. As being said, we have so many different types of the Warmix asphalt technology, and there's many benefits provided by the Warmix asphalt. As we can see the photo here that are demonstrating that a Warmix asphalt technology providing much better working environment for the field workers. As also you know that Warmix is initially comes from the Europe and is getting very popular in the US. But our concerns about the long-term performance of Warmix, we are not sure about what's going to be going on after 10 years of the Warmix in the field. So that's going to be the objective of this research. We want to compare HMA with the Warmix. Looking at a long-term performance, we also want to know what's going to be the critical material properties that could have significant impacts on the long-term performance of Warmix. So this is going to provide us a much better understanding of the Warmix technology before we confidently and fully use that. So the overall, we are looking at 28 field projects across the US. As we know, US, we have 4 major climate zones, including dry freeze, wet freeze, dry non-freeze, and wet non-freeze. We have 22 in-service projects and 1 heavy vehicle simulator in California. So totally we have 40 HMA and WMA payers, ranging from 4 to 9 years pavement age. We also have 5 newly constructed pavement section, including 8 HMA WMA payers. So based on those field projects, we monitor performance. I want to discuss that major distresses in terms of the transverse cracking. As we can see that for transverse cracking, we also find that there are both reflection cracking and surface initiated cracking. So this is indicating that the transverse cracking is not only about the thermal cracking related, but also maybe as a reflection. So another major type of distresses we find is going to be the wheel path longitudinal cracking. So we also take the field core at the tip of the crack. We slice the core into different layers, and we can see that the crack is going to starting from the top and propagating downward. So this is indicating that wheel path longitudinal cracking, they're all the top-down fatigue cracks. So the third major distresses we find is the rotting depth, but however, we find that the rotting depth is very low for both WMA and HMA pavements. So besides the distress survey, we also collect a lot of field cores for each pavement section. We do the binder extraction. We also do a lot of testing on the bitumen in terms of PG grading, G-star percent delta, etc. For the asphalt mixture cores, we run the IDT modulus. We also run the IDT fracture testing at room temperature and low temperature, which one is the 20 Celsius degree, one's the negative 10 Celsius degree. We also did a Hamburg wheel tracking device on the field cores. And Hamburg wheel tracking testing can also provide us moisture damage resistance of the asphalt mixture. So based on the field data, I want to present you the results and what's the finding in terms of the comparison between the WMA and HMA. So the first one is about the Butamine properties. So we are using the PG increases, which is calculated by the extractor binder PG minus the original binder PG. So in this figure, what you can see that the WMA is in blue, the HMA is in the red. So WMA Butamine developed a long-term field aging slightly more quickly by showing more number of data points. We also found that a WMA was produced at a lower temperature than HMA initially. Under the long-term field aging, WMA Butamine was catching up and experienced more rapid oxidation and aging. So the next one, we are going to focus on the asphalt mixture properties comparison between HMA and WMA. So this figure showing the number of WMA and HMA pairs with respect to the percent differences in the dynamic modulus. So you can see the majority that the WMA and HMA, they are pretty much comparable in terms of the stiffness. The second figure is showing the IDT strength and a fracture work density comparison for the HMA and WMA. So, and also we can see the majority, they have very similar material properties here, indicating HMA and WMA showing a similar top-down cracking resistance. So in terms of a low temperature cracking resistance, we are using the ITT fracture work density comparison as well as the ITT strength. What you can see here that in the majority, plus minus 10% comparison, the HMA, the WMA has comparable and a better thermal cracking resistance than the HMA. So the last one is about Hamburg wheel tracking testing. So we are using that rotting resistance index. So what we can see that a majority, the WMA and HMA, they are showing very comparable rotting resistance. So in terms of the field performance, as we can see for the top-down fatigue cracking, with more aging, you're gonna see more cracks. As comparison between the WMA and HMA in terms of the top-down fatigue cracking, they are showing very comparable performance. So for the transverse cracking comparison, what we can also see is that with a longer pavement aging time, we're going to see more crackings. And also we're going to see the HMA and WMA showing very comparable transverse cracking resistance. For some of the projects, they are showing early age transverse cracking, most likely is due to the low temperature in fact. So for the rot depth measurement, as you know that HMA and WMA, they are showing very low rot depth. If you're going to calculate the difference between the HMA and WMA pavement section, it is a very low number, as small as 0.01 millimeter. And this is indicating that HMA and WMA section has very comparable rotting performance. So based on our finding, I want to recap what we found for this project. From the material property point of view, after long-term aging, both asphalt and bitumen in WMA and HMA have been aged. They are showing very comparable stiffness, ITT strength, and fracture work, low temperature cracking resistance, as well as rotting resistance. From the field performance point of view, pavement that are using the WMA showing very comparable field performance as compared to the control HMA section in terms of the top-down fatigue cracking, transverse cracking, as well as the rotting. So based on our finding, we found that WMA can be confidently used to have the same long-term performance as long as the mix design is followed in the similar manner as the HMA design. So last, I want to thank NCHRP 9-49A project to sponsor, and also Dr. Harrigan and a panel member for their insightful perspectives, as well as many industry partners and universities participate in this project to provide a valuable field performance data as well as the field course. So finally, I want to conclude my presentation. I also want to mention that if you want to know more information about our project, we published a final report, a long-term field performance of Warmix asphalt technologies. This is the link to download the final report. So now I'm open to any questions you may have. Thank you.
Cheng-Hua. And I would now like to invite the three presenters of the second section of session 7A, that is Fernando, Carlos, and Cheng-Hua, to join me for the questions and answers session. But before we start with the questions and answers, I would like to express my deepest gratitude and appreciation for the technicians in the background, which nobody sees. I'm always happy when it's not only me having issues, but thank you very much for solving this so easily and so fast. I'm grateful that we do have these digital tools available, but then just like human beings, they are not without failure. So thank you very much again. Thank you for the audience, for your patience. By the way, you are 176 right now in this room. Let's start with the question and answers. Fernando, I would like to address or forward two questions to you, please. The first question is about whether you have considered maturation time during the production of the rubberized bituminous binder, and if yes, please explain the condition, that is how long and at which temperature. And the other question is about the concentration of the crumb rubber in the asphalt mixture, including the size of the particles.
Thank you, Anya. Good afternoon to everybody. Well, about the first question, in this case, in this particular application, it was not necessary any maturation time because we have used a refinery chrome rubber modified asphalt binder. So it came directly from the petrochemical industry. So the chrome rubber was already reacted when we introduced the binder into the asphalt plant. Anyway, we have many years of experience on the application of these modifiers, and we could say that in our experience, it was not as a key issue the maturation time that you can achieve in the transport time, the hauling time from the asphalt plant to the job site. The key issue when you are using chrome rubber outside the asphalt binder, in this case, I'm talking about the dry process, could be the design of the mixture and the manufacture of it. You cannot consider an introduction of the chrome rubber in weight, because the density of the chrome rubber is much lower than in the aggregates. And the problem that you are going to have is that you are introducing so much volume of chrome rubber on the mixture. So that could be much more important than the maturation time. If you are considering any particular maturation time, you are including an impact in the manufacture of the asphalt mixture, and you are putting barriers in the application of this technique. About the second question, what the amount of chrome rubber used in the modification of the bitumen, in this particular case, the amount was around the 5%. We have tested the amount of final chrome rubber that we obtain in the mixture, and we obtained variable result that was from 2 to 6% of chrome rubber content over the weight of bitumen. It was a very, very adverse condition that we have applied this asphalt mixture. It was the first that we did inside this project. We were a little bit scared of using higher amounts of chrome rubber because of problem in storage stability of the asphalt bitumen that it came from the refinery. And so what we did is to use around 5% over the weight of the bitumen in chrome rubber, and we have combined it with SBS polymer. So indeed, it was an hybrid chrome rubber SBS polymer modified binder.
Okay.
About the size, for sure, you should use less than 0.5 millimeters of the particle size when you modify the asphalt bitumen.
Okay, thank you very much. And maybe you can discuss more details if there are more detailed questions on that offline. Everybody can contact you, I know. Carlos, I would also like to ask a question to you. And I think it was your clothing slide where you mentioned as the second of the 3 bullet points that you are aiming to assess the carbon footprint savings. How will you do that?
Well, that is a challenging, ambitious challenge. But at the moment in Australia, the AFPA, the Australian Flexible Pavement Association, is really undertaking this job. They are developing EPDs, environmental product disclosure for the mixes, and all industry is coming together. So really, that was my ambition when I started this journey and when I was putting together the presentation. But in the last 2 years, there is a lot of work that has been done by AFPA and all suppliers. So really what from my perspective will be to use that material, that all these tools that they are developing, and trying to assess what are the savings and what are the difference between a standard practice or a Warmix practice. Yeah.
Okay. Thank you very much. I'm eager
Cheers.
to follow that.
Yeah.
Shenghua, there's a question to you which is pretty highly ranked, and that is Vincent is curious about the top-down fatigue cracking you observed, as we usually associate fatigue cracking to be from bottom up. Are such top-down cracking load-induced or more related to environmental degradation?
Okay, thank you for the question. So essentially, this project is about the long-term performance. Those projects that's been in the field for at least a couple of years. So the one that we observed for the wheel path longitudinal cracking, and also we take a core at the tip of the longitudinal cracking, and we found that essentially that a crack was starting from the top and it's going to propagate downward. So that's based on our observation that the top-down cracking on the wheel path is going to be essentially starting from the top. I know that traditionally when we talk about fatigue cracking, it's going to be starting from the bottom, because we have a tensile strength at the bottom of the asphalt layer, and you're going to see the cracking propagating upwards. You're going to see the alligator cracking. It's going to be determined by the area. But the one that we saw essentially is going to be because of the I would say it's because of the 2 things. One's going to be environmental impact. Another one's going to be the high shear zone, due to the tire, on the wheel path. So that's just going to explain that essentially, the mechanism of the top-down cracking on the wheel path. And we are trying to compare the Warmix, versus the traditional hot mix in the long term. So we are trying to look at, different distresses like a rotting, fatigue, and moisture damage, as well as their transverse cracking. For particular top-down cracking, as we observe, HMA and Warmix, essentially they are pretty much comparable. So this is going to give you more confidence, to use the Warmix, because earlier that people had a hesitation, to use the Warmix, a new technology.
Thank you very much, Shenghua. I'm very sorry that I need to interrupt you here, but the clock is ticking down, and I'm reminded that we only have limited time. Thank you very much. Thank you very much to the presenters, to Fabrizio, to Mario, to Torsten, to Fernando, Carlos, and Shenghua. Thank you very much to the technicians. Thank you very much to 239 participants in this session now. And now enjoy the keyword coffee break. See you later. Bye.